Let us take few examples. We have this. Suppose we have the sets like set of all complex numbers, all complex numbers z such that mod z is strictly less than 1. Then set of all complex number z such that mod z is less than equal to 1. Then C is a finite set. D is say set of all integers. Is the set consisting of the number is like this, the set of all complex numbers, set of all complex numbers, set of all numbers of the form say 1 by n, where the n belongs to n natural number, okay, or numbers of this, and E f set of all complex numbers, and then the segment A B, the segment A B. Let us see the example and see whether these sets are closed, which are open, whether they are closed, whether they are open, whether they are perfect, or whether they are bounded, because these concepts we have already seen. Now, you see the first one, obviously it is not closed, because closed means the set is closed when the mod of z is less than equal to 1. 1 is the point which is the limit point of this. So, it will not be a closed set. So, this will not be a closed set, no. So, here is no. Then it is open, because mod z less than, every point will be the interior point, it will be open. Then perfect set, the set is said to be perfect if it is closed and every point of it is the limit point. Since mod z is less than 1 is not an closed set, then obviously it will be a not be a perfect set. And then bounded, yes, it is bounded by 1, means all the point of z is less than equal to 1. So, it is a bounded set. This set, yes, it is closed, because all the points which are this limit point all belongs to it. The limit point of C is a point of this, limit point is there. It is not open because of the closeness, it is not open. Perfect, though it is closed, and then whatever the every point, whether every point is the limit point or not, yes, it is inside the disk mod z less than equal to 1, every point is an interior point when mod z less than 1, and 1 is also the limit point in it. So, it will be a perfect set. Then bounded, yeah, it is bounded because 1 is the finite set. Finite set, it does not have any limit point. So, we can assume all the limit point inside it are there. So, we can say it is closed, but it is not open. Why it is not open? Because the finite set, when you choose, these are the sets, point. So, if we draw the neighborhood around the point P, then we do not get any point other than this. So, this will not be an interior point. So, it will not be an open set. Since it is closed, but no limit point. So, we can say this set is not perfect, because every point must be the limit point. Perfect set is closed and every point of P is a limit point, but every point is not a limit point. So, it is not, and then of course, it is bounded, because only finite number of there, we can identify a point, find out its distance from this particular point. So, you can find a m upper bound. So, that this is bounded. Set of integers, this is closed set, again the same thing, set of integers, the point, every point is not a limit point, because again there is a gap between 1 and 2, there is a gap. So, we can draw the neighborhood around the point 1, which does not include any integer. So, 1 cannot be limit point. Similarly, all other integers did not have a limit point. So, set of integer does not have a limit point, but we can assume all the limit points inside it. So, we can say it is a closed set, say D, okay. But it is not open because the point are not interior. So, it is not open. Then it's perfect. Again, every point is not a limit point, so it's not a perfect. And whether this is bounded or not, obviously this is 1, 2, 3 is an unbounded set. We cannot find a n, so that all the point is less than equal to m. So, this is not bounded. Then set of all numbers 1 by n, 0 is the limit point for this, except 0 no other point is the limit point for this. So, this set is not closed, E is not closed, because closed means all the limits point belongs to this, because 0 is not a point in it. So, 0 is a limit point which is not n. So, it is not closed. It is not an open set. Why? Because the point 1, 1 by 2, 1 by 3, they are not the limit points. They again they are not an interior limit point, therefore, it is not open. It is not a perfect set. However, it is bounded, because the bound is upper bound is 1. Set of complex number is an entire set, we can say all the limit points are inside, as well as every point is the limit interior point, because we can draw the ball around each point, which is totally contained in the complex plane. So, it is open. So, it is open closed. It is perfect also, because all the points are limit point, every point is a limit point. So, we can say it is perfect, and then bounded set is no, because it is unbounded plane. Segment. Segment is not an closed, because it is an open segment, it is an open set, but when you say the segment A B, then the openness depends on the topology on the set. Suppose I take A B as a subset of R 1, then it is open, then it is open. But if we take A B as a subset of R 2, then it is not open. Why? Because it is not open, because every point of this set is not a interior point. The reason is, in this case we can choose this is a set A B, whatever the point you choose, you can draw the neighborhood around that point, which is totally contained in it. But in this case, the A B interval is this is our A B, and the neighborhood, when you take, the neighborhood will be something like this. So, here the points are available here, which are not the points belonging to this set. So, we can say this point cannot be an interior point. So, similarly others. So, it cannot be an open set. It's then it is not open. It's not open set in R 2. So, that is important for this. So, that is why we are not a, and further perfectness is not there. So, we can say cross, and then bounded, yes, because its bound is A B. Whatever the topology you take, it bounded. So, you can this. So, this way we can identify. Now, here this shows, this example shows that openness or closeness are relative concept. Say the set which is a subset of a set, which is the set of which it is a subset. So, with respect to that, whether it is open or not. If we consider A B as a subset of R, then obviously it is open, but when you consider A B as a subset of R 2, then it is not open. So, it is a relative concept. So, we can further give a definition of the openness or closeness with respect to the set, that is called the relatively open or relatively closed sets. So, we can okay. Now, the results are further. So, we have another results theorem. The theorem is a set E is open if and only if its complement is closed. Complement means that is if X E is a subset of X, X D be a metric space, then complement of this means denoted by E C, which is X minus E. Complement of this set is closed. Okay. So, proof is, so let us suppose E C is closed. Suppose the complement of this set E C is closed. Then what we want is to show E is open. Required to prove is E is open. It means every point of E is an interior point. So, choose an element x belonging to E. If I prove that there is a neighborhood around the point x which is totally contained in E, then E becomes open. Okay. Now, since x is in E and E complement is the set of those points which are not in E. So, clearly x is not an element of E complement. Okay. And so, x is not a element of this. Now, further x is not a limit point of E complement and x is not a limit point of E complement, E complements. Okay. So, is why is not a limit point of the E complement? Because the reason is E complement is closed. E complement is closed. So, closed by definition, all the limits point must be the point of the set. If set is closed, if it includes all of its limit points. So, if x is not in E C, so x cannot be limited, because if it is a limit point, it must be the point of E C. So, here is this E and this is our space x d and here this is E C. So, we are taking a point x here which is in we are taking x here. Now, what we say is x is neither in E C nor is a limit point of E C. Okay. So, there will be some neighborhood around the point we can draw which is totally away from E C or does not intersect with E C and lies in it. So, there exists, hence there exist because it is not a limit point. It is not a limit point. So, we can find out a neighborhood around the point x which is totally away from E C or intersect of E C is empty. So, there exists a neighborhood n of x such that the neighborhood n of x such that intersection with E C is empty. Okay, because it is not a limit point, and if it is a limit point, then every neighborhood of x must contain some point of E C. So, since it is not a limit point, we can identify a neighborhood whose intersection with this empty. We do not have any point inside this neighborhood. That is, the neighborhood is totally contained in E, because it contains only the points of E. Okay. So, what they show that x is a point around which we have a neighborhood n which is totally contained in E. This shows that E is open. This shows x is an interior point of E. Hence, and x is arbitrary, but x is arbitrary point of E. So, every point has is an interior point, therefore, E is open. Clear? So, this shows the concept. Conversely, suppose E is given to be open. Conversely, let us assume E is open. We wanted to show the closed E C is closed. Okay. So, to show E C is closed. So, we wanted to prove that all the limits point of the E C are the points in E. So, let x be the limit point of E C. E C. Okay. If either once it is the limit points, and every neighborhood of x will include the point of E C. So, every neighborhood of x, every neighborhood contains a point of E C. So, once the every neighborhood contains the point of E C, it means x cannot be an interior point of E C, because if it is an interior point, then there will be a neighborhood around the point x which is totally contained in E, but every neighborhood contains the point of E C also. So, this shows that this neighborhood, this x cannot be an interior point of E, cannot be an interior point of E. Okay. The further what is given is E is open. Further, since E is open, so what do you mean? It means if x is a point in E, then because E is open, so x must be an interior point, but here we have shown x is not an interior point. Therefore, this implies that x cannot be in E. So, this implies that x will be in E complement. So, it will be an E complement. This follows that E complement is closed. That is what is proved. Okay. So, now as a corollary of this, we can corollary, a set F is closed if and only if its complement is open. Complement means F is a subset of X, complement means F C, which is X minus C, is closed, is open. Okay. Now, this proof goes just the previous, from the previous theorem we can derive this corollary easily, there is no point of wasting time. Now, following results holds for any collection, G alpha of open sets, where alpha belongs to the index sets, the union of G alpha when alpha belongs to I is the index set, alpha is in I is the index set. Okay. Then G alpha is open. This is one. Second result says for any collection F alpha of closed sets, the intersection, arbitrary intersection, this is arbitrary union, arbitrary intersection F alpha, alpha belongs to I is closed. Third, for any finite collection G 1, G 2, G n of open sets, the finite intersection of these open sets is open. D is for any finite collection, F 1, F 2, F n of closed sets, the finite union of these F i's is closed. So, here this C and D is not valid for a arbitrary or infinite collection or countable intersection of G I and countable union of F I is not valid, may not be true. Okay. So, only for finite case is true. The proofs again follows like this. It is given that each G alpha, for each alpha is a open set. We want the arbitrary union is open. So, let us take a point, let x belongs to the arbitrary union of G alpha, alpha belongs to this. It means that then x will belongs to G alpha for some alpha, belongs to I, but G alpha is open, is an open set. So, there exists a neighborhood around the point G which is totally contained inside it. So, x will be an interior point of G alpha, that is there exists a neighborhood and with set suitable radius delta such which is totally contained in G alpha. Hence, this neighborhood and x delta will also contain in the countable union of G alpha. So, this implies x is also an interior point of union G alpha, alpha belongs to I, but x is an arbitrary, point. So, what we say that countable union of G alpha is open, because every point becomes the interior point. So, this implies that countable union G alpha, alpha belongs to Y is an open set. Similarly, for the part B follows from this result. We know this is a simple set theoretical result. Arbitrary intersection of this, if I find the complement of this, this becomes the arbitrary union of the complement of this f alpha c. Now, what is given is f alpha is closed. So, f alpha c will be open, since f alpha is closed. So, this implies that complement of this f alpha c is open, and right hand side is the arbitrary union of the open sets, right hand side is open. Therefore, this implies the left hand side will be open. So, this implies the left hand side is open. So, complement of complement is closed. So, this implies that arbitrary intersection alpha belongs to I is closed. That proves. Then second C part, we wanted to show that finite intersection of the open set is open. So, let us take H as the finite intersection of G I is 1 to n, where G i's are open sets. So, let us take the point x belongs to H. Let x belongs to H. So, this implies that x belongs to G I for each I 1 to n. Now, each G I is open. So, there will be a neighborhood around the each G around x with a suitable radius r I. So, we can say so there exist neighborhoods n I of x with radii r I, where I is 1 to n, such that the n I, this neighborhood is contained in G I when I is 1 to n. Means each n x is in all G I. So, for each I there will be a neighborhood n I which is totally contained in G I. Now, choose the radius r, choose r as the minimum of these r 1, r 2, r n. So, if we draw the neighborhood, then the neighborhood with a center x and radius r obviously will contain in G I for each I 1 to n. Therefore, it will contain this intersection, contained in the intersection which is H. So, this shows that H is open. H is open. Okay. The second part follows in the same D, that is finite collection is like so. A B C D, D follows as earlier. So, Now, let us take the case when there are infinite intersections. So, C and D do not hold for arbitrary intersection and union respectively. The examples are, suppose I take the G n as minus 1 by n, then these are all open sets, but the intersection of G n is 1 to infinity is the singleton set 0, which is closed. Similarly, if we take the say our f n as say 1 by n and 1, these are all closed sets. The arbitrary union of these f n's n is 1 to infinity is the semi closed interval 0 to 1, which is not closed. So, this shows the arbitrary intersection, they are not true. Okay. Now, we define the concept of the sets. Okay. If X is a metric space, and if E is a subset of X, and if E dash denotes the set of all limit points of E of X, then the closure of E is the set denoted by E bar, which is E union E dash. So, closure of this. So, what is this is closure means, suppose a set E is given, then set of all limits points, if I include it in E, then the collection will be known as closure. So, closure of the set is the set which includes all of its limit point as well as the point of E, of course. Then there is a result. Theorem is, if X is a metric space, and E is a subset of X, then the closure of this set E bar is closed set. B, if E is equal to E bar, that is then if and only if E is closed. And third is, if E bar is contained in F for every closed set F which is contained in X, such that E is contained in F. It means that is E bar closure of this is the smallest closed subset of X that contains E. The proof is simple, just I will give the first proof. A, E bar is closed, E is given to be this, then closure of this is closed. So, let us say if P belongs to X and P is suppose not in the closure, okay, then P is neither a point, P does not belongs to S, as well as P is not a limit point of this, So, once it is not there, so there exists a neighborhood, n which does not intersect with E. So, if does not intersect with E, then complement of E bar is therefore open. Therefore, E bar is open. The complement of this is open. EC is open, then the complement is C of E bar C is open, complement of E bar C is open, and this shows E is closed. This shows E bar is closed, sorry, this shows E bar is closed. So, that is second and third part follows very easily. So, we are just dropping and getting. Thank you very much. Okay.